Thank you very much for inviting me here. This is a very exciting session. Today I'm going to talk to you about neuromechanical principles that allow us to understand how muscles are coordinated for movement. And I wrote this with the help of many colleagues and collaborators, and I'm going to give you just the highlights today. But if you're interested, we wrote this article where we tried to synthesize a lot of the ideas from a large body of work amongst all of us. So first of all, I'm interested in how interactions between the nervous system and the biomechanics of the body shape how we move. And particularly, the types of paradigms that I'll be showing you today are shown here. I started by looking at reactive balance control, both in an animal model, the cat here, where the platform moves. We also study those things. I think I should use the cursor here. No, that's not going to work. There we go. Okay, so we also have the person here, where we move the platform, and we can study the motions, but more importantly, the muscle activity of the body. And we extracted principles about how the nervous system and the mechanical system interact. Now, you may be familiar with the idea of task-specific plasticity, which means that when we learn things, it shapes both the interactions between the nervous system and the biomechanical system. And to look at that, instead of training people, we look at people who are already trained in some sense. And here I'm showing you a walking task, a challenging walking task. This is a ballet dancer from the Atlanta Ballet. We want to compare that to this is an undergraduate student from Georgia Tech, probably, doing the same tasks. And what we hope to gain from looking at these types of activities and the muscle patterns is some principles about how the muscle activity is organized and how it changes through training as we increase the ability of people through training, but also by looking at impaired individuals. So what I'm going to do today is show you, this is an outline of what I'll talk about, outline some neuromechanical principles. Hillel Scheel, my co-author, really challenged me to write down some principles for people to think about. Then talk about this idea of modularity and how can we use that to understand neural control of balance and walking. How are these altered with training, whether you're a ballet dancer or if you're a person with Parkinson's disease who goes through rehabilitation. And then at the end, if we have time, I have a little bit of new work on studying principles of human physical interaction for rehabilitation. And all of these principles, I think, are really important to think about when thinking about rehabilitation, either through traditional therapy, through robotics, or through neuroprosthetics. So first, what are these neuromechanical principles? Here we are, and the take-home message is that if we just look at the biomechanics, we really cannot determine the muscle activity. And I learned this the hard way because I started graduate school as a mechanical engineer thinking we could solve the problem simply by writing down these equations of motion. But those are important and they will drive what we see in muscle activity, but how many of you have collected biomechanics, so kinematic data, and muscle activity, and then looked at the muscle activity, and then you don't publish it? Because it's highly variable in the muscle activity, and that's why these principles are really important to understand. Why is the movement so regular, but the underlying neural control signals in the muscles so variable? So here, I'm going to go through this a few times, so you'll see this slide a few times, but the idea is there are many, many different solutions that the biomechanics allows us to produce. So there are some constraints by biomechanics, but that's not the whole story. So the biomechanics and energetics matter, but we have to look beyond just what's the optimal, especially in a patient population. So the energy isn't everything, and I'll show you some ideas about multifunctionality, but the upshot of the whole thing is that these properties allow people to be individuals, to have individual motor accents, I call it, or motor habits that allow us to recognize differences in how people move, and this may really affect what kind of training will improve their movements, right? So I'm going to introduce the idea of that we're sloptimal and we're not optimal. So what can we learn from mechanics? This is a recent study in which we wanted to say, if I understand the biomechanics of the system, how much does it constrain muscle activity? And this is an OpenSim model. It's a standard model. You can download it on the internet, and you can take some measured motions of a person walking, and we said, well, how much does it determine how you have to activate your muscles? Typically what happens is we take these measured activities, put it through some kind of energy optimal cost function to determine muscle activity. But it doesn't say how much my muscle activity could differ from that optimal. And in fact, when we take data, we actually see that people do differ. So this is a question that Bernstein actually posed about a century ago. And what he said was that if I take a measured movement over time, the force that's generated by muscles cannot be uniquely determined, but it may have some bounds on the activity over time. And this is just taken from his book. And we wanted to say, what do those bounds really look like during a functional task like walking? And we asked the simple question of how high or how low can each muscle be activated while achieving these set of joint torques that we actually observe experimentally. And so here's the result, which is that here's 6 different muscles over time during walking. The upper boundary is the black solid line, and the lower boundary is this other thick solid line as well. So what that says to me is that although the optimal low energy muscle activity, which is shown in blue here, has this particular pattern which picks up some of the features that we see in measured muscle activity, which is in red. In reality, I could probably either turn one of these muscles all the way off or all the way on and still be able to achieve the task, assuming that I could change the activations of all of my other muscles independently. So what it means is simply that if we observe one muscle to not follow this optimum, it doesn't mean that the person didn't actually achieve the task. So we have to look a little bit more carefully. And this is just to say that for walking, it's very unconstrained from biomechanics. So then if you look at multiple patterns that produce the same task, this is a simple example from a cat hind limb generating a force, you can choose patterns that are more or less unstable. So the minimum energy solution often makes the limb go very unstable, which poses a very high neural control challenge if you wanted to control that limb. So it could be adding a little bit of non-energy optimal activity could allow you to stabilize the limb, and in fact this movie on the right is the most stable. It's not very interesting because it doesn't move, and you may not want your limb to be going unstable when you're trying to control it. If we look further, this is again the cat musculoskeletal model, and say, can we interpret motor output by looking at a single muscle's activity? The answer is obviously no. We have multiple joints and they need to be coordinated. And what we can learn from a biomechanical model is that if we activate one muscle, say here the posterior biceps femoris, and we want to look at the actions produced at the toe here, the arrows represent the sort of acceleration or the force that's generated at the endpoint, and we can see that when I activate posterior biceps femoris, you can generate a backwards and upwards force if you completely immobilize the ankle, but as you reduce the amount of torque generated at the ankle, you can actually direct that force into different directions, where it could be more forward and more backward. What that tells me is that the specific relationships in activation between two muscles are extremely important in forming movements. And because we have so many muscles that can be combined in 2 to the n ways, it's not true that we could necessarily just search or compute the answers, but in fact, they might need to be remembered through experience. So if you think about learning how to move and finding a combination of muscle activity that actually allows a baby to move their arm to the left or to the right, that those specific combinations of muscle activity are extremely important in having a biomechanical function. So simply by looking at biomechanical models, which is what we did here, we were able to demonstrate that there are many different solutions, again, that can be found for any particular problem, and that while the biomechanics is important, there are a lot of other considerations for how muscles might be coordinated, where they might deviate from an energy optimal. And again, I'm going to propose to you that this results in having individualized movement patterns, but that are still unified under a set of principles. So understanding that, how can we use that information to understand neural control of balance and walking? And I'm going to tell you how we can tease out individual differences and look at variability as well as generalization across tasks. So many of you may be familiar with this idea of motor modularity and the idea that we're not using all different random combinations of muscle activity, but very specific sort of patterns of muscle activity that can be reused to produce specific muscle biomechanical outputs. And why would we do this? The motor modules that I'm going to talk about today really are talking about just the very lowest level of coordinating multiple muscles at one instant in time to move the limb. What that does for the neural control signal is it allows me to structure a control over time that doesn't have to think about muscles, that thinks about what the task is, whether I have to move to the left, move to the right. And so that temporal, the decision making that you have to do on a very fast time scale can be done at the level of the motor goal that I want to achieve and not necessarily thinking about individual muscles. So that's why we think that they're useful, and that from a neural control point of view, this type of hierarchical arrangement has been shown in spinal cord control of locomotion. So what does that actually look like when we think about it? Here is a figure demonstrating what I call motor modules or muscle synergies on the left, when a cat is standing on the platform like I showed you, and we move the platform in different directions in the horizontal plane, and we study the structures that are consistent across all of those different directions that the animal is falling, right? So on the left here, on the bottom, we have muscles, and each bar represents the particular level of activation of a muscle that's required, that we observe to be consistently produced. And we identify these through factorization techniques. What you'll see is that there are a large number of muscles that are coordinated, and as I mentioned before, their relative activation is important. And if you look at any one muscle here, you can see that it can participate in many different modules. So we're always using the same set of muscle actuators, just reconfiguring them in different ways to produce movements. This activation level here, the bottom, is the direction that the animal is moving and the level of recruitment of each of these modules. And what we are able to show is that each one is preferentially activated to restore balance when the animal falls in a particular direction. And we can further decompose the biomechanical outputs, and that is the forces at the limb endpoint here. And so the activation level of this motor module is directly correlated to the production of a particular endpoint force. So this allows me to transform this idea of pushing, generating force in a particular direction simply by activating this remembered pattern, and it can be done flexibly combined. So I have one that goes down, one up, one forward, and one backward. And together I can generate the full repertoire of movements to restore balance in these different planes. And now these motor modules are in fact predicted through engineering principles by energetic optimization. But in reality, what we see is that each animal expresses their own individual structure of how they produce that movement. So here on the top, I have muscles. The red ones are the ones that are collected in the same muscles for each animal. And you'll see that for all of these animals, this red motor module produces the extensor force that allows the animal to stand and to bear weight. This tall bar here in each of them is the vastus. It's the quadricep muscle, the extensor that is biomechanically necessary to allow the animal to stand. So that's our biomechanical constraint. Says if you don't have this muscle on, you're not going to be able to achieve this task. But if you look at the hamstring muscles here, whoops, on the left, you'll see that the amount that those muscles are active in each animal are different. So this is where that flexibility comes in. I can turn the muscles on a lot or a little bit. And what we find is that these patterns are recruited in the same directions of falling, and they generate the same types of outputs. So the input and the output of, to these are the same. They're used in the same functional way, but the specific way that they're implemented are different, and this is the idea that people and animals prefer these habitual rather than optimal solutions because they're reliable. And perhaps the animal on the right is perhaps more stable and a little bit more cautious than the one on the left. That's just a conjecture. Now, when we do the same type of analysis in human subjects, we also see that there are a number of, see, Sandro, using this cursor is messing me up. The muscle synergies here we have more, and they might correspond with different strategies that humans have of using a hip strategy or an ankle strategy for balance. One of the things is that the motor muscle activation patterns for doing a hip strategy and an ankle strategy are quite different, and we can have different mixtures of these two strategies at any time. Looking at what analyzing the muscle activity using factorization allows us to do is not to average in these two very disparate types of motor patterns, but to be able to extract how much ankle strategy or how much hip strategy is being used from one trial to the next. So this allows us to look at trial by trial variability within an individual to see how that individual is changing the way they control a task, but considering their subject-specific way of coordinating muscles. So once we take out the subject-specific nature of the coordination on the left, we can look at the variability, this is from one trial to the next, of how they're actually using that on the right, and therefore we can take out averaging. And this is extremely important in looking at a clinical population because people differ in how they move from one trial to the next, but the underlying control structures could in fact be similar. So we can extract principles about movement and to understand how each individual is remembering how to do the same task, what seem like very similar tasks on the outside. So the trial by trial variations are not just random variations in muscles, they're task-dependent variations. If you look further, you can see that the same modules used for one task could be shared across another task. We've done a whole series of studies looking at reactive balance, which is an automatic brainstem-controlled activity, as well as walking, and have shown in many different ways that you could use a common set of modules to do walking, recover from perturbations, stiffen the leg, and that in general, we can identify modules that are recruited based on what direction you want to move your body center of mass, whether it's in balance or in walking. And so this is why I say that the modules may be the lowest level of motor organization, so one step up from muscles, that allow flexible control of lots of different types of movements that are nonetheless specific to each individual. Okay, so that was a fast tour of the modularity, and so the idea is that the modules are these control points that allow you to change the motor goals that you have into actual muscle activity. And this idea that we might have lots of different representation using the same set of muscles was actually proposed by Hewlings-Jackson in 1889, talking about how as you go up through the nervous system, They're re-representations of movements. And if you think about the muscles as sort of notes on a piano, you can combine those in many different ways to generate a large repertoire of movements. And if you think about a particular, each composer may have preferences or styles that come out. So the basic way to think about these modules is that they are a stored repertoire of these motor actions that we have that may allow us to do different movements, adapt them very quickly without having to think about things. And we have to think about these in order to then look at changes in motor control as people develop through evolution, training, and disease. So how are these modules altered with training? I'm going to show you whether you want, however you want to alter somebody's movement through robotics, virtual reality, prosthetics. We have to think about this task-specific neuroplasticity. And I'm going to show you two studies we did. I'll see how many results we can get through. First, we look at ballet dancers. These are highly trained professional ballet dancers, and we wanted to see how their muscle activity differs. On the other end of the spectrum, we use the same techniques to look at a set of patients with Parkinson's disease who go through a dance-based rehabilitation. In this case, it's adapted tango. So we wanted to know, well, how does ballet training refine motor modules for walking? And why is it that we can tell a ballet dancer when they're walking, even when they're not dancing? So this is just to show you that when they walk across the beam, they're better at it, and their kinematics between the experts and novices are fairly similar. But the long-term training from the ballet dancers increased how consistently the muscle coordination was activated. So here are the motor modules, and we do this mapping, which preserves the distances between the modules from one trial to the next. And all this shows you is that if you look at the motor modules recruited by the experts, they're much more consistent and distinct than the ones we see from our undergraduate students. And this is during the portion of the beam when they're not falling off. Okay, so even in that time when they look like they're doing the same thing, they're not really doing it the same way. So the experts are using these very well-learned, distinct solutions where the novices maybe look like they're doing the same thing, but their muscle activity is a little bit off. Similarly, if we look at the Parkinsonian patients before and after this training, actually the number of motor modules, so the variability actually goes down as well. So here you can see that this cluster of orange is tight, but it's even tighter after the rehabilitation. Each of these dots is tighter. And then this yellow one that's spread out all over the place is actually just gone, right? So by using these modules, we can show that the patients, even though you wouldn't necessarily think to compare them to these ballet dancers, the principles of what consists of better muscle coordination is actually there in both of these populations. Okay. The experts have less muscle coactivation than novices, so they're more optimal and we're more sloptimal. The other take-home message is that if we look at the people with Parkinson's disease, they don't necessarily reduce coactivation because they first need to learn a useful motor pattern, and if they have that motor pattern, they can refine it. But if they don't have that motor pattern and they have to learn how to do a new action, then they will actually reduce, they won't reduce the muscle coactivity right away, but perhaps with more training, that could happen. I'm going to skip this one because it's harder, but what I wanted to do is here are the last messages, which is that the abundance of motor solutions usually is thought about as a problem for engineers, right? So we have to find the one answer, and people actually use lots of different motor patterns for whatever their different reasons are, whatever types of activities they do. We need to consider that when we're thinking about any kind of engineering solutions that are going to affect how people move. And so individualized motor solutions that people may have could affect how the same intervention might differentially affect one individual versus another individual, and the differences in how we train them could also affect how useful a learned pattern is across multiple tasks. So by sort of appreciating this abundance of solutions, we could build engineering solutions that could more generally help a wider range of people across a wider range of diseases with different experience. So with that, I will stop and thank my funding sources and other collaborators. And if any of you want to come to study healthcare robotics, we have a new PhD training program in that area. So thank you.